Yeah, this looks like a positive charge. Now, it looks like a positive charge, and the vector field then, instead of representing the velocity of a fluid, could just be the E field. So yeah, the divergence of the E field is actually positive in regions that contain positive charge. Now, does this look like the E field from a point charge?
Yeah, a positive charge.
Not exactly a point charge. Why not? What should the E field do if that's a point charge at the center?
Decrease.
It should be getting weaker with distance. This one's getting stronger. Have you ever seen a place where the E field starts out at 0 and then it gets stronger as you move outward?
Yeah.
Inside a uniformly charged region, yes. So what I've drawn, if I label these vectors E field, I've drawn you the E field inside a region that's full of positive charge. If I just had positive charge at the center, the field would actually grow weaker as I move outward. It turns out here's one of the four Maxwell's equations. The divergence of the E field is 1 over epsilon naught. You remember epsilon naught, it's the ugly cousin of K Coulomb. Historically, epsilon naught how we write Maxwell's equations, even though I kind of would prefer 4 pi K Coulomb there. But you get 1 over epsilon naught times the charge density. And again, if I've got a region where the charge density is uniform through the whole region, I get this kind of hedgehog effect. I get the E field growing stronger as I move outward. If I have a point charge, it turns out I've got positive divergence at the center. And then as I move outward, the E field gets weaker. And it might look as if that's negative divergence out there, because as I move in the X direction, EX is growing weaker. And that doesn't make sense. I don't have negative charge surrounding my point charge. Well, remember, if I'm, say, standing at this point near a point charge, if I move in the X direction, EX does get weaker. That gives a negative contribution to the divergence. But the divergence is a scalar. I add together these 3 contributions. I don't consider each one separately. If I move in the Y direction, and again, assume this is a point charge right here. If I move in the Y direction, what's the E field going to be looking like?
It's going to get weaker.
It'll get weaker if I move far enough in the Y direction, although at first, since I'm kind of moving perpendicular to the distance, it won't be getting that much weaker. But what will I notice at first as I move? The E field won't really get stronger or weaker, but it will change direction. It'll be pointing away from that charge. Notice if I move in the Y direction, the E sub Y is increasing in the positive direction. If I move in the negative Y direction, E sub Y is increasing in the negative direction. This is spiking a positive result for this Coulomb's law E field, just as this is spiking a negative result. And it turns out that Coulomb's law, that 1 over r squared dependence, is actually the only function I could have put in for the E field where those 2 things turn out to cancel one another, and I'm getting 0 divergence everywhere away from that central charge. In fact, if this whole thing was a region that was like inside a charged sphere, as soon as I leave that charged sphere, now the E field's going to start growing weaker as 1 over r squared. You all know that. You know that from Gauss's law. But it will turn out that once I'm outside that sphere, the divergence of the E field is actually 0 everywhere. So here is your first of the 4 Maxwell's equations. Now, since we've just got a couple minutes left, I will still get you through 2 of the 4 Maxwell's equations, because you can probably tell me, what is the divergence of the B field, the magnetic field? When have you seen a case where the magnetic field diverges outward from some region? Point charge, the electric field points outward. When does the magnetic field do this same thing? When does the magnetic field point outward from some region? If I have a bar magnet or something like that, I can say, yes, from the North Pole of that bar magnet, it looks like the magnetic field does point outward. From the South Pole, it looks like the magnetic field points inward. However, the magnetic field does continue through the center of the magnet. Is the divergence, does the North Pole, is that actually a source of B field lines?
Not
No.
The B fields always wrap around in a circle, as it turns out. If I were to draw a Gaussian surface around this, yeah, I've got B field lines pointing outward, but on this side I've got B field lines pointing inward. What would we call a situation where the B field did just point uniformly outward from some region? Magnetic monopole. And to the best of our knowledge so far, they do not exist. So, tentatively, until the triumphant day when we discover the first magnetic monopoles, the second of Maxwell's equations reads this. It's telling the B field never diverges outward from a point. There is no such thing as magnetic monopoles. Now, if it turns out that there are, Maxwell's equations are very well prepared to deal with them. It just means I will replace that zero with some constant times the magnetic monopole density. And the constant just depends on what units we decide to measure magnetic monopoles in whenever we actually find the damn things. But for the moment, that second of Maxwell's equations is zero. Now, when we talk about vector calculus, if I say, oh yeah, it's like div, grad, curl, and all that stuff, I still owe you one more fundamental function or operator of vector calculus, which is the curl operator. This is what's going to happen when I take this same old del operator and I cross it with a vector field instead of dotting it with a vector field. And again, we'll go through the same thing. I will ask you, how would I artificially build myself a vector field that has a curl in such and such a direction? And we'll sketch one out on the page. And then I will ask you, when have you seen that in the context of electromagnetism? And it will turn out that, probably no big surprise, the curl of the B field is an interesting thing to talk about. That would sum up the second third of this class. And the curl of the E field is yet another interesting thing. That sums up Faraday's law. So again, the fundamental rule, the Biot-Savart law and Faraday's law, I can write both of those in the language of curls. Just like Gauss's law and the absence of Gauss's law for magnetism, I wrote both of those things in the language of divergences right there. All right, more on that next time. I will also give you the divergence theorem and the curl theorem, and then once we have all of Maxwell's equations out there, we'll see what we can do with them.